Okay, so let's learn a little bit about electric circuits. Um, some key concepts. First of all, voltage. We've already talked about it. It's the ratio of energy per charge, and its units are joules per coulomb or volts. It's otherwise known as potential. And to get some insight into why voltage makes current flow, let's look at what happens inside a voltage source, say this Duracell. Now what makes the negative end negative is excess negative charges, say excess electrons, due to the electrochemical reaction at this end. What makes this positive end positive isn't excess positives, instead it's a lack of electrons that have disappeared into the wire at this end. So if you could look with microscopic eyes, this is what you'd see when you looked at a Duracell. Excess negatives here and a lack of negatives at this end. Now the way we draw this in circuits is like that. That's a circuit symbol for a voltage source. Now, to help understand what's going on in electric circuits, it's helpful to have a mechanical analogy. So here's a simple circuit where you've got a source of energy and then some sort of load doing something useful, maybe a light bulb or a motor. And we can think of that as being equivalent to a ski hill. So the lift here is a little bit like the source of voltage, the cell. And then the ski run is a little bit like the resistor. And charges going around the circuit are a little bit like skiers going up and down the mountain. So now that we've got this idea that a voltage source, say like a Duracell, is excess minuses at this end and lack of minuses at this end, we can imagine that if we hooked a wire up, that the excess minuses here are going to push on the minuses that are already in the wire. And they're going to make them move away because, of course, like charges repel. So the minuses in the wire will shift. So they're repelled by the minus end of the cell. So those charges will shift to the end of the wire. But that motion is only going to be momentary because very quickly the repulsion from this end of the cell, which would tend to push the charges away from it, that'll be canceled out by the repulsion here, a small buildup on the end of the wire. So I should say the negatives in the wire are repelled by the end of the cell, and they flow momentarily, but only momentarily, the order of nanoseconds, and then the flow will cease altogether. Now, if we have a continuous loop, then those minus charges, which are the only things that can move, will get pushed all the way around, and then here there'll be an electrochemical reaction that sucks them up. So you don't get that balancing pressure, so here you'll get the sustained flow of charge, where the minuses in the wire will be repelled by the minuses at the negative terminal of the cell. And the sustained flow of charge is called current. Now there's a problem with that circuit, as we'll see later. There's no resistance to flow in that circuit, and that tends to create large currents, which, if this is just a battery, will just deplete the battery. Now it doesn't take much, just a tiny little wire bent around into some loops and then put inside an evacuated glass chamber, i.e. a light bulb, will provide some resistance, and therefore will keep the current, or will limit the current, and hopefully to a safe value. So current is that flow of charge that we were just looking at. So it's the voltage that made it flow, and the current is defined as the charge flow per unit time. Now we don't care if those are positive or negative, current will have positive magnitude. Now remember that charge is like money. Any charge can be broken down into a certain number of fundamental charges. So let's do a simple current example here. So here's a typical dry cell, a 1.5 volt, and they have ratings. Now what does this rating tell us? So we see it's 0.75 amp hours. So what is an amp hour? Well, amp is the unit of current. That's an ampere. and clearly hour is a unit of time, and then current times time, we see from our definition, is a charge. So this is really telling us the Q. So if we've got 0.75 amps, an amp is a coulomb per second, and an hour is 3,600 seconds, we can see in coulomb units that that dry cell is storing 2,400 coulombs of charge. Now, how many electrons is that? Well, charge is like money, so that charge can be broken down into fundamental charges, but no smaller. So how much? That 2,400 coulombs. Remember, the fundamental charge is 1.6 times 10 to the minus 19, so we see this is an astronomical number of fundamental charges, 10 to the 22. But then that's only, that's even less than 1/100th of a mole, right? Because a mole would be 6.0 times 10 to, sorry, 1/10 of a mole. So what is it? Yeah, so anyhow, it's a fraction of a mole, right? 6.02 times 10 to the 23rd. So it's a 10th, and then divide by 4. So it's a 40th of a mole. Okay, how long will the cell power the motor? Well, the motor in our portable music device draws 0.25 amps of current. So we want to find the time. So we know that current is charge over time. So we cross multiply time up and current down. And we see that we can calculate the time in this way. So we've got 2,400 coulombs stored in our cell, and we're drawing 0.25 amps or 0.25 coulombs every second. So that will last then from 9,600 seconds, which is 2 2/3 hours, which sounds about right for a dry cell powering a portable music device. Now, we said that an electric circuit was like a ski hill, and here charges gain energy and flow around the circuit. Here skiers gain energy and then flow down the hill and then get back on the chairlift again and again and again. But there's a small problem with that analogy, and that is just that the electrons actually flow uphill from lower to higher, and most things in physics flow downhill. So we have a conceptual problem, and what we choose to do is to come up with a convention, which is to say, instead of focusing on the flow of the electrons, let's imagine that we just focus on the flow of positive charges. Even though it isn't the positive charges that move, the electrons moving to the left is just like the positive charges moving to the right. So what we're going to call current then is actually the downhill flow of positive charges. The actual motion of the electron flow will be opposite to that. Let's see what I mean by that. So here, well, we know which way skiers flow, right? In a gravitational circuit, it goes that way, up the hill and down the hill. We know that electrons would actually get pushed this way around the circuit. They'll be repelled from the negative terminal and attracted to the positive. But what we're going to call current, I, flows from positive downhill to negative or lower, and then in the negative terminal. So current is opposite to the direction of the electron flow. Now in practice, that sounds confusing, but in practice it's not a problem, because what we're going to call current is just going to be the flow of positive things, and very quickly we won't talk about electron flowing anymore. Now every circuit offers some resistance to the flow of charge. This is a symbol for a resistor, and where the resistance comes from is the fact that as the electrons, or as the current moves through this resistor, the electrons would really be going the other way, they bump into things. They have collisions with atoms, and therefore they lose some of their energy, as we've seen in the momentum unit, and that gets transformed to heat. So voltage, remember, is energy per charge, and losing some energy, therefore, is like losing some voltage. So you go from higher voltage to lower voltage as the charges flow through. Now, the principle that governs that is known as Ohm's law, and we're going to write a word equation for that. So we imagine having a high amount of resistance, and if you have a high amount of resistance, then that's going to give you a small flow of current, because it's going to be hard for the charges to get through. So there won't be very much flow. If the resistance is less, there'll be a large flow. What that suggests is that current flow, I, varies inversely with resistance. Okay? It says write a word equation, so I better write a word equation. So there we go. So when the resistance is big, the current flow is small. That's characteristic of inverse variation. Now, if you've got lots of voltage here, lots of stored energy, then clearly you're going to have a large current. And with a smaller voltage drop, you will have a smaller current flow. So what that suggests then is direct variation between current and voltage. So current then varies directly with voltage, inversely with resistance, or as that is usually written in its cross-multiplied form, V is IR. So we're going through the very basic circuit properties. And what we've got so far then is we've got our definition of voltage as energy per charge. We've got our definition of current as the charge flow per unit time, Q over D. And now we've got our, I suppose, our definition of resistance in Ohm's law. Now, Ohm's law for ski hills, the resistance is like the depth of the snow. And so with high resistance, really deep snow, the flow of skiers will be slower, right? So flow is inversely proportional to resistance. So deep snow means less flow. Hard packed snow is like a small resistor. That's going to give you a large flow. And the flow on the ski hill is proportional to the height of the mountain, because with a higher mountain, skiers go faster and therefore there's more flow. So this is what Ohm's law looks like for ski hills. And there it is there. So skier flow is the height of the mountain over the snow depth. Okay, so we'll just use Ohm's law and do a really simple calculation. Remember, current comes out of the positive terminal, flows through the circuit, and back into the minus terminal. So because V is IR, we can rearrange that and say current's voltage over resistance. So we had a 6-volt cell hooked up to a 25 ohm motor. And so that is 0.24 amps, or 240 milliamps of current. Now, if you didn't have that motor in there, if it was, say, shorted with just a wire, then that same 6-volt cell with 0.001 is suddenly tasked with providing 6,000 amps. And most dry cells won't provide that, so you'll just deplete it entirely, and it will be a dead cell. If you were to short circuit something with the capacity to produce that much current, like car batteries can produce hundreds of amps, then you will get that much current flow. The wire will heat up and it will melt. If that happens in the walls of your house, because BC Hydro can also provide really large currents, then those wires will melt and potentially start an electrical fire. So this is called a short circuit, not because of its length, but because its resistance is gone. It's going to create a hazardous situation. With no resistance, you'll get huge unsafe currents. Okay, so voltage, current, resistance. Some other key electric circuit concepts are power, energy, and efficiency. So power, well, we were talking about the fact that there's a loss of energy as current flows through a resistor, just due to collisions and electric friction. And so some of that electrical energy is getting converted to heat energy, and we just want to find an expression for that. So, in fact, we'll find an expression for the energy now. For the power, rather. Power is energy over time, and because a voltage is an energy over a charge, we can cross-multiply and say that energy must be charge times voltage. So there's charge times voltage over time. And then we're just going to rearrange that a little bit. I'll pull the voltage out here, and then I'll leave Q over T over there by itself. The reason we do that, of course, is that the charge flow per unit time is the current. So we see that the electrical power is the product of voltage and current. And we should check the units there just to make sure this is in watts. So a voltage is energy per charge, so that's in joules per coulomb. Current is charge over time, the coulombs per second. So multiplying those two things together, we can see that coulombs would cancel, and we indeed end up with joules per second, which is the definition of a watt, and is therefore a proper unit for electrical power. So, the rate at which electrical energy is transformed to heat energy then is given by the product of voltage and current. Now we can substitute in Ohm's law there and get some other versions of that. So for voltage, we can put in IR, and then I times I gives us I squared R. That's one version of that. The other version substitutes in for current. Now if you solve this for current, it'll be V over R. And now, multiplying that, we can get V squared over R. So these are all equivalent expressions for electrical power. Now, household circuits are 120 volts, and appliances have power ratings on them. So if this is a 1400 watt hairdryer, we can find the current, because we've just said that electric power is the product of voltage and current. So the current will be the power over the voltage. So this is a 1400 watt hairdryer hooked up to 120 volts. And so what have we got there? That'll go in once, leaving 20, so that should be a sixth. So sorry, one more time, and then 0.6 amps. So about 12 amps of current. Now most household circuits are limited to 15 amps, so you couldn't put very much more on this circuit or you'd pop a circuit breaker. Here's a mix, oops, sorry about that. Here's a mix and match exercise where you're going to take appliances and, so for instance the computer, well let's start with the easy one. So the clock is probably the lowest power draw, that's just 0.1 watts. So mix and match all the other appliances in your home with the approximate power rating, because you should have some sort of idea for how much energy these things are using. Now, we were just calculating electrical power, but we can work out the total amount of energy used, because of course that's what you pay for. Because power is an energy over time, we can find an energy by multiplying the power and time. Now, energy is typically in joules, but a joule is a really small unit of energy when we're talking about, say, electrical power consumption. So we'll use a much larger one. We'll express the power in kilowatts and the time in hours. So a kilowatt hour is an energy unit. Now, how much is it in joule terms? Well, a kilowatt means 1,000 watts, and an hour is 3,600 seconds, and a watt is just a joule per second. So the seconds would cancel. It ends up being joules. So it's 3,600 times 1,000. It's 3.6 million. So a kilowatt hour is 3.6 million joules. So here's a calculation I did a number of years ago in the midst of a roommate conflict. I was chastised for leaving a light bulb on one night by mistake. Usually I turn them off. I'm quite obsessive about that, but one night I forgot. And so I just did this little calculation to tell my roommate there wasn't very much to worry about. So a 60 watt bulb, so that's using 60 joules every second. That's the power of the bulb. And we leave it on all month. Okay, so that's 30 days, 24 hours in a day, and then 3,600 seconds in an hour. And we want to find the amount of energy it will use in joules. Well, energy is the product of power and time. So we're using 60 joules every single second, and then we're multiplying by this time here, right? 30 times 24 times 3,600 in second units. And it turns out that that's 1.55 times 10 to the 8 joules, or 155 million joules, which sounds like a lot. But remember, a kilowatt hour is 3.6 million joules, and this is not that many kilowatt hours. Now, we could do the conversion, but here's a sort of a neat trick. We're going to express the power in kilowatts. So 60 watts is 0.06 kilowatts, right? That's 60 watts of power. And then we're going to express the time in hours. Now, 30 days, 24 hours, that's actually 720 hours. Now when you multiply this together, you're going to emerge with kilowatt hours directly. 0.06 times 720 is 43.2 kilowatt hours. Now, electricity is cheap. It's only about 6 cents for a kilowatt hour. Now that's gone up a little bit. You know, the lowest step on the sliding rate scale is about 7, and the higher step is 10, but let's just use the old number here, 6 cents per kilowatt hour. This is from a few years ago. And then we're using 43.2 kilowatt hours if we leave it on for the entire month. That would be about 259 cents, or $2.59. Not very much. So I recall at the time, I think I taped a couple of loonies on the fridge and said, here, this will more than cover the night. I don't think they appreciated the calculation, but the math does not lie. The concept of efficiency we've seen before. It's the ratio of useful output to input. So here's a calculation for you to try, and just pause the video and give it a try, and then you can have a look at my answer. Using the ratio of power to voltage, that's a little untidy there. Ohm's law gave us the resistance. Efficiency is the ratio of output to input. We were told that the useful output is 58 watts, joules per second, of heat and light for every 60 watt unit of electrical input. So that's 97% efficient when we consider both the heat and the light from that bulb. With the light only, it's only about 2% efficient, but light bulbs are actually pretty good heaters. Energy is power times time, so I did that trick where I expressed the power in kilowatts and the time in hours, so that gave me 0.48 kilowatt hours. 6 cents each gives me about 3 cents of cost. So that's an introduction to some basic circuit concepts.